Okay, welcome to the third edition of the video to study for the upcoming test we have with Mr. Burke and the Math 110 class at Crafton Hills College. We're going to take a look at question 12 now, and I already wrote down some information which you'll probably want to include in your cheat sheet, as I hope you'll find it helpful. I'm not sure how clear the book is on this, but I'm going to try to bring some clarity to this topic, which is very important for hypothesis testing, that you should have some greater clarity about. So we are, when doing hypothesis testing, going to be making a comparison between two numbers. The first number is, I'll mention, is known as the critical value, which is obtained on the outer edges of a normal distribution, whether we have a 10% level of significance, a 5% level of significance, a 1% level of significance. Because what we're doing is we're looking at the normal distribution and we're trying to establish at what point we're going to either not reject the null or we're going to reject the null. So at the 10% level of significance, and I'm going to treat this as, for the point of convenience here, I'm going to treat this as a two-tailed test. If we have a 10% level of significance, what we're saying is that looking, and this is probably a little big, but that we're looking at 90% of the area here, where the 10% level of significance would consider that the area of these two pieces here combined together would be 10%. If we're looking at a 5% level of significance, then we'd be looking at a normal distribution, and my graphs are not the best and this should not be touching this axis here. We'd be looking at 0.95 of the area being here, like we would for the confidence interval, where the remaining two areas here are going to be 0.05. If we're looking at a 1% or a point, like a 1% level of significance, then we'd be looking at the area of this part here being 99%, and then the other remaining portions being 1%. What all these three graphs have in common is that each of these is going to produce some type of z-score. And the z-scores at these boundaries are what we're going to call critical values. So each of these will produce a z-score depending on the circumstance. And the boundary we have for each of these is what we call a critical value. Meaning that if we get a test statistic, which is something we obtain based on the data that we collect from our sample, if we get a test statistic that is beyond the range of these critical values, like if we cross beyond this point, we cross beyond this point, we cross beyond this point, we have a situation in which we say that it doesn't seem likely that we would be out this far if we accept this as being true. Therefore, we're not going to accept it as being true, and therefore, we will reject what has been established as the null hypothesis. Now remember, we never accept the null hypothesis, we just fail to reject. In the situation in which the absolute value of the test statistic is not greater than the critical value. Okay, so if we get a test statistic within this region, then that's not surprising, or that wouldn't be considered unusual. However, if we generate a test statistic outside of the region defined by the areas here, then what ends up happening is we say that's not likely to happen unless something is wrong with this, and we're going to conclude that we're going to reject what is established as the null. But remember, we never accept the null. So in question 12, I have just a couple formulas here. And these can go in your cheat sheet. And a lot of times students will get confused about the negatives and positives we get, depending on what side of the tail that we're on. And so I have these formulas here where we're going to take the absolute value of C sub 0, which is going to be the test statistic, and compare that to the Z of alpha, or Z of alpha divided by 2. The Z of alpha here, this is a one-tail situation, or the Z of alpha divided by 2 is a two-tailed situation, which establishes the critical value. So if the absolute value of the test statistic is greater than the absolute value of the critical value, if this is true, we end up rejecting the null. So if this is true, we reject the null hypothesis. If this is not true, we fail to reject. And this is what question 12 is asking us. So question 12 is inquiring about, is the level of significance necessary to make that determination? So in question 12, they ask that a survey claims that 9 out of 10 doctors, or 90%, recommend brand Z for their patients who have children. To test this claim against the alternative that the actual proportion of doctors who recommend brand Z is less than 90%, a random sample of doctors was taken. Suppose the test statistic is Z equals, so we have a test statistic in this question of Z equals negative 1.95. Now, in the question itself, you'll notice that there's not a 0 because that notation of using the 0 is not a universal notation for test statistic. But since they are telling you it's a test statistic, you may use that. Can we conclude that the null hypothesis should be rejected at the 10% level of significance, at the 5% level of significance, and at the 1% level of significance? So if we're going to do this, let's establish what we need for this now. So I'm going to move this up a little bit here, and I'm going to make these different comparisons. So I'm going to say, is the absolute value of 1.95, is that going to be greater than the Z of 0.10? I'm going to leave a little room here. For B, is the absolute value of negative 1.95, is that going to be greater than the Z of 0.05? And then for C, is the absolute value of negative 1.95, is that greater than Z to the 0.01? Now, the reason I'm using this one and I'm not dividing it by 2 is because they want to determine if it is less than 90%. Because it's less than 90%, we're in a situation that that's going to represent a one-tailed test. So what we need to do is, and hopefully you're comfortable with this, is we need to go to the table to find each of these values in order to make a fair comparison. So we want to go to the table to find the closest value to 0.1 that we can. So for this one, we're going to use a z-score table. And you notice that I did some of this work ahead of time. So the closest one we have is this like 0.1003. And the z-score that generates is going to be negative 1.28. So that's going to be here, negative 1.28. And we'll see here that 1.95 is going to be greater than 1.28. So based on this test statistic, we would say that this is true. Therefore, we would reject the null hypothesis based on what we have here. So let's take a look at 0.05. Let's find this area on the graph here, or on the table. And I found this to be that at 0.95, that this is going to yield a z-score of negative 1.64, and it's going to be like right between here. So it's going to yield a test statistic of negative 1.645. Now, if you're not perfect with this and you choose one over the other, that's okay. It won't really make a difference in the final answer anyway. We'll have here that 1.95 is greater than 1.645, because if you choose either value, it's still going to be true. So this is true. Therefore, we will reject the null in this case. In the case of z to the 0.1 level of significance, I have looked this up here again too, and we found we get a z-score of roughly negative 2.32. So I'll put that here. So I have z-score negative 2.32, and I compare that to negative 1.95. And I'll see here that negative 0.195 I put is greater. I know that's not true, but I'm just going to put this. Well, negative 1.95 is not greater than 2.31. Therefore, this is false. Therefore, I fail to reject the null hypothesis. So for the first two situations, for the 0.1 level of significance and for the 0.05 level of significance, we do in fact reject the null, but in the last case, we do not. And you'll find that the answer that that's going to yield is going to be choice A for question 12, which I indicate right here. So you definitely want to make sure you have your z-table for that. Please be sure to check online in an announcement I sent yesterday regarding the test information. I've included the identical charts that I'm going to provide to you for testing, so that way you can get comfortable with those charts. So if you need to work with those or learn how to work with those, you'll know what you'll be looking at. Okay. We're going to go to question 13 now. It says determine the critical value for a left-tailed test of a population mean at the negative 0.025 level of significance based on a sample size of n equals 18. Okay, so when they give you that sample size of 18, that should hopefully tip your hat to let you know that this is going to be utilizing a t-table. Okay, so for this one, what we want to do is we want to go to the t-chart I have here. That's chi-squared. Here we go. Okay. There are a few things you need to know about this in order to do this question properly. If they're giving you the significance of 0.025, one thing we need to account for too is that if n is equal to 18, remember that, and I'm not sure if the book uses this particular notation, but DF stands for degrees of freedom. And this is something that we use with the student t-distribution because the shape of a t-distribution changes depending on the value of the sample size. And we know that the higher the value of n, the more it approaches a normal distribution. The way we determine the degrees of freedom is to simply take the n value, and at least in this case, we'll subtract 1. For different applications, there are different ways to determine degrees of freedom, but in most, it's always going to be n minus 1. So if I do that, that's going to be 18 minus 1. So that's going to give me 17 degrees of freedom. Okay, and the other number I want to account for is where alpha is equal to 0.025. So utilizing the table that I provided for you online in the announcement, we find 17 degrees of freedom. We find for a one-tailed test where it is equal to 0.025, and we yield the number 2.11. And in this case, that's going to be choice C on your test sheet, or in the answer sheet there. So confirming that that's correct for number 13. Or excuse me, not 2.11, but negative 0.211. And the reason it's going to be negative 2.11 is because that's a left-tailed test. So you always have to watch out for that when you look at the tail of the test, because since it's left-tailed in terms of the distribution now, this is a t-distribution, so usually we get something that looks like this when we do a t-distribution. If it's a left-tailed test, that means we're going to the left of here, so the z-score, the t-score in this case, is going to yield a negative value. Okay, let's go to 14 now. Let me put this up here. Okay. A local tennis pro shop strings tennis rackets at the tension pounds per square inch requested by the customer. Recently, a customer made a claim that pro shops consistently string rackets at lower tensions on average. Okay, so on lower tension, so this isn't not equal to the tension requested, it's lower. So that should indicate a one-tailed test. Let's keep reading them. To support this claim, the customer asked the pro shop to string 6 new rackets at 42 psi. Suppose that the two-tailed p-value for the best described above obtained from a computer printout is 7. Give the proper conclusion for the test of 0.05 at the 0.05 level of significance. So now the reason they talk about this being a two-tailed test, because if we're going to reject in the case of a two-tailed test, we'll certainly reject it for a one-tailed as well, because you'd have to go further to the left if that were the case. So let's go ahead and take a look. So